All right, for our second unit today, we're going to start looking at the last section in chapter 18, which is about solids. And the going to give more of an introduction today, and then tomorrow we'll get into the actual work and calculations that you need to know for the quiz and for the final exam. But we would just want to kind of set the table up for tomorrow to make it a little bit easier conceptually to understand what's going on. So when we talk about solids and solid properties, we have to understand proximity, closeness is really at the kind of bedrock of what this is all about. And so the forces between the atoms and the molecules, the ions, whatever it is that is holding that solid together, are really strong. Strong enough that the particles are in fixed positions, where because they are in fixed positions, they're going to have vibrational degrees of freedom, but they're going to have little to no translational or rotational degrees of freedom. Um, Again, close proximity is going to play a lot of role in that, and the inability of those atoms to move. Now, you can get into a discussion, and this is where I would largely defer to our geosciences department in terms of all the different directions that we can go with solid classification. But um, we're going to kind of focus mostly on crystalline solids, which are those that have structured, regular, repeating patterns to them. But there is another class of solids known as amorphous solids. And these are ones where we have much more random distributions of the atoms and the molecules. This is where we get into things like waxes or tar asphalt or even glass. So understand that there are other kinds of solids that exist, but we're going to spend most of our time in that bottom category, the crystalline solids. And the reason for that is because they are more ordered and structured, we can actually do more with them in terms of calculation, prediction, and those kinds of things. And so just to kind of give you a visual representation, the figure here on the left is an example of, at least in terms of the atomic arrangement of what an amorphous solid would look like versus a crystalline solid on the left, or on the right rather. You can see that the crystalline solid is extremely ordered, very highly arranged. And so from an entropy standpoint, very, very low entropy, as you might expect here. Whereas because of the somewhat scattered and more randomized arrangement of that amorphous solid, you're going to have higher entropy in those solids comparatively. Now, when we start getting into discussing the different kinds of crystalline solids, we do want to know that there are some subcategories and distinctions among them. So, for example, molecular solids. Molecular solids exist when the thing that is repeating is molecule. So, a good example of that would be water, snow, ice crystals, where we have a solid that is being composed of these very ordered arrangements of molecular compounds. And the thing that is holding these molecular compounds in place are intermolecular forces. So that's what a molecular solid is. That's what a molecular solid looks like and how it's held together. Metallic solids, on the other hand, those are ones that are composed of metals and metals only. Every solid metallic element on the periodic table is a metallic solid. Now, with metallic solids, we will talk about order and arrangement with those a lot more precisely. That's where a lot of the calculations that we're going to do for this part of the chapter come from. But the crystalline nature is what it generates. So we've got crystals here of osmium. We have crystals here of gold. Ionic solids, these are solids that are made by just the electrostatic attraction of the positive ions and the negative ions to each other. And again, they fall into similar kinds of patterns to what we see in terms of the metals. And so there's going to be a lot of overlap. So when we talk about metallic structure and metallic properties, we'll see that ionic compounds tend to follow similar kinds of patterns. And as a result, we get a lot of similar kinds of crystalline appearances and structures here. So on the left here, we have rock salt, sodium chloride. This very clear crystal here. And then on the right, one of my favorite compounds, copper 2 sulfate, just that bright royal blue color. And again, crystalline in its composition. The last common type of solid is something called a covalent network solid, or just a network solid. What we see in these is kind of a weird blending together of covalent properties and intermolecular forces. So in both cases, so here we have two different examples of carbon. We have diamond on the left and graphite on the right. Now, both of these qualify as covalent network solids. What you have in diamond is basically a structure, a setup where every single carbon in that structure is bonded to 4 other carbons and bonded covalently to those 4 other carbons. And because everything is bonded to everything else and it's all covalently stuck together, what you end up having is an incredible strength in these molecules that makes them very, very hard as minerals. This is why diamond is one of the hardest materials known to man. Graphite, on the other hand, graphite exists in these two-dimensional sheets where an individual carbon atom is bonded to 3 others, basically. And the sheets are attracted to each other by intermolecular forces so that they kind of slide over each other. Now, the resulting compound, the resulting material for graphite is not terribly strong. As you know, if you use a real pencil or even a mechanical one, the graphite that you use to actually write with the pencil is extremely fragile. Cracks on you, breaks on you, snaps in the middle of your test answer, or smears all over your Scantron sheet and you have to go erase everything. That's one of the properties of graphite, is its brittleness. But its free movement of electrons, because there's that free motion there, graphite actually does a really good job of conducting electricity, or at least a reasonable job for most covalent compounds. Now, the thing about network solids, there aren't many of them. There just aren't. They're mostly fixed to things that are non-metallic, that have a way of relating to each other in some kind of way. For the most part, they just don't exist in a lot of different ways. So the four types of solids that we're going to focus on in this discussion of crystalline solids are the molecular solids. These are soft solids. They do not conduct electricity. Made up of molecules held together by intermolecular forces. And because of that soft nature, because of that relatively low attachment, these molecular solids tend to have low melting and boiling points. Metallic solids, on the other hand, we have a variety of soft and hard. They conduct electricity really, really well. They are packed together pretty tightly. And as a result of that, they do have relatively strong intermolecular forces between them, which makes them really hard to melt, really hard to boil. They have very high boiling points and melting points as a result. Ionic solids are brittle because they are not bound together quite the same way, with quite the same packing and strength as a metallic solid is. But because of their charges, they do conduct electricity when they are melted or when they are in solution. We've seen examples of both. And because they are attached to each other by relatively strong intermolecular forces, they definitely have an elevated melting point compared to the molecular solids. And then the network solids, these are mostly hard substances, although graphite and graphene are a little bit of an exception to that. They don't conduct electricity for the most part, but graphite and graphenes do. So graphite and graphene are kind of the exceptions of these, but they're also probably the most interesting. Because with graphite, you get a lot of electrical conductivity kind of things. And graphite becomes kind of the framework and basis for graphene structures. Graphene structures are at the genesis of what are called carbon nanotubes, and spurred an entire subset of nanotechnology. This extremely hard to read table, even on my screen, does give us an idea about melting point and melting point trends. And it is in large part very similar to what I was explaining before. The molecular solids have really low melting points. The metallic solids and the covalent network solids tend to have a lot higher melting points. And then the ionic solids kind of exist in that middle space where they certainly are not as tightly packed or associated as the metallic ones are or the networks are, but they are definitely more attracted to each other and have far better properties than the molecular solids do. So with this in mind, we've got four different compounds here on the board. Match them to each other. So we've got calcium chloride, we've got ammonia, we've got diamond, we've got calcium. To which classification of solid do they belong? So lining them up, this should be relatively easy. The categories are pretty distinct from each other. So calcium is the only metal that is just a metal on this list. So that would be our metallic solid. Ammonia is the only true non-metallic substance that is also molecular. Diamond is non-metallic, but it's not molecular. It's atomic. So that goes there. We did talk a lot about about diamond being a covalent network solid. Calcium chloride, well, this makes sense. It's an ionic compound. It would be an ionic solid. All right, so the last thing that we want to talk about today, kind of setting things up for tomorrow, is the idea of kind of crystal lattices. So we said that we were going to spend this solids time talking mostly about crystalline solids. Well, crystalline solids form what is called a crystal lattice. That crystal lattice is the organized, ordered structure of the compound or the ion or whatever the solid is made out of. Every crystal lattice can be broken down from this wide array of lots and lots and lots of molecules, ions, atoms, whatever, to a single simple repeating unit called a unit cell. So it doesn't matter what the crystalline solid is, the crystalline solid can always break down to the simplest idea, which the simplest idea is something called a unit cell. And so if I take the unit cell, which is that simple building block of a crystal lattice, and I multiply it and replicate it over and over and over again, I would get the crystalline structure for that substance. Now, unit cells get classified by their symmetry. And I'm going to show you a slide that shows a lot of the different kinds of symmetry that exist. What I want you to understand is that we're going to focus primarily on three shapes, and those three shapes are going to be symmetrical. They're going to fall into a cubic kind of arrangement. So some things to know about unit cells before we get into greater details. We can describe something called a coordination number. A coordination number for a crystalline solid would be if I pick out any atom in that unit cell, any atom in that crystalline structure, the number of other atoms that it is touching is the coordination number. Now, for ionic compounds, it's a little bit different because they aren't always touching each other. They're kind of affiliated with each other. So for ions, we talk about how many of the opposite charge are they in contact with. Higher coordination numbers mean greater interaction. Greater interactions mean stronger attractive forces to hold the whole thing together. And that generally means a couple of things, usually. It usually means that we have a more dense solid, and that more dense solid usually has a higher melting point because of the increased attraction. This is closely related to something called packing efficiency. Packing efficiency is the volume percent of a unit cell that is occupied by actual particles as opposed to empty space. And the higher the coordination number is, the more efficiently the particles are packed, the less empty space there is. And again, with higher degree of packing, we usually will see higher densities. We'll also usually see higher intermolecular forces, which means higher melting points. So here's our first unit cell type. It is called a simple cubic. Simple cubic because all it is just something called square packing. And it's exactly what it sounds like. I have a single row of atoms and I just layer them on top of each other directly. The unit cell for this looks like this over here, where I can just see that if I were to try to overlay onto this, I would have just a simple cube where at every corner of the cube, I've got me an atom. Every atom touches 4 other atoms. So we've got a coordination number of 4. Relatively, yeah, relatively straightforward, the model here. Now, one thing that we will talk about, so with unit cells, one thing that we will talk about, especially tomorrow, is the idea that the unit cell itself kind of overlays on top of the of other unit cells. And so if I'm looking at this atom right here on the top left corner, I need to understand that that atom is being shared by a total of 8 different unit cells. How do I come up with 8? Well, we know that it's in this unit cell, but we also know that it would be in the unit cell directly to the right or directly to the left. We know that it would be in the unit cell that was up here to the front and left. And we know that would be in the unit cell that's here in the front to the right. So that's 4 unit cells that it's in. And we haven't even considered that, well, it's in the top of this unit cell that we can see. It's going to be in the bottom of a bunch of unit cells as well. So every single atom in this simple cubic model is a part of 8 different unit cells. And the significance of that is going to become important when we start to compare this kind of unit cell to other kinds of unit cells. So here's a slightly better version of what I just drew. And so we can see we've got the 1 unit cell here representing this corner here. If I look at any of these, I can see, okay, well, this one here, in addition to being a part of this unit cell grouping here, That one in the back would also be a part of this one that I'm labeling in green. This one that I'm labeling in light blue. And this one that I am labeling in yellow. So it's in each of those four. If there were a layer on top of it, it would be involved in 4 unit cells in the layer on top. And so for simple cubic, we say that each unit cell contains a total of 1 atom. How did we come up with 1 atom? Well, we've got 8 corners. Each corner is in 8 different unit cells. So that means that each corner is 1/8 in this cell and 1/8 in all the other cells. 8 corners times 1/8 is 1. 1 atom in this unit cell. A second type of unit cell is something called body-centered cubic. Body-centered cubic atoms start with 8 atoms on the corners, just like simple cubic, but also 1 in the center. And so what this stacking pattern looks like is called an AB pattern. So instead of the square packing where each layer is on top of the other layers, on top of the other layers, the in-between layers fit in the holes in the spaces between. So if we go back to here just for a second, what we would see in body-centered is that instead of packing on top here, on top yellow on top of yellow, we would pack that next group in this hole created by the 4 atoms. We would put another one in this hole created by 4 atoms, another one in this hole created by 4 atoms. And then the next layer, which isn't shown here, would replicate the first because the holes in this would happen to also be exactly where the first layer was in the first place. So this is body-centered cubic. And so from a stacking pattern, from a counting pattern, we see a lot of similarities to the simple cubic, but with this extra piece here in the middle. Put those together, and we would end up with, we get 2 atoms per unit cell in this pattern because we've got the 8 corners, so 8 corners times an eighth, that's 1 atom. And then we've got the atom that's trapped in the middle of that box, so a total of 2 atoms per cell. Now, one thing that we need to understand, your book and these slides are showing these in different colors so that you can see the different layers. What we need to understand is that these are all the same substance. So if osmium is body centered, then all of the layers are osmium atoms. They're just arranging themselves in a different way. So, this is showing it as grays and blues and peaches. Understand that this is all the same thing. So if I'm looking at a metal that does body centered, every single one of those circles that you're seeing there, they're all the same thing. They're all iron, or they're all cesium, or they're all iridium, or whatever it is that is body centered. The last arrangement that we're going to talk about is the what's called cubic closest packed, CCP. Now, the result of CCP is something called face-centered cubic. Now, CCP does what is called ABC layering. And what happens in ABC layering is this. Basically, there are 3 different layers that are made. The middle 2 layers are basically opposite triangles sandwiched to each other. So if you can imagine one of them forming a triangle that points toward you, the other one is going to make a triangle that points away from you. And when you put those 2 layers together, they're going to fit kind of each other's holes. The third layer, which is being shown in yellow, fits in the holes on the top and bottom as well. This is why it's called closest packing. Usually things that end up doing this ABC kind of stacking pattern are usually smaller. And the reason that they can get away with it is because of their size. Because they are smaller, they're capable of doing more. They're capable of packing together closer and making these tighter arrangements. Now, the face-centered cubic arrangement itself graphic is wrong. What we end up seeing, and again, with the coloration here, it's difficult to kind of discern. But what we see is the same cubic pattern. So there's my simple cubic. And I'm going to use different color here again, not because it's a different substance, but just for showing each one of these faces on the cube is sharing another atom. So I have the 8 corners times 1/8. So that's 1. And I have the 6 faces. And since each of those atoms, each of those faces is only in one other unit cell, then that means that half of this one is in this cell, half of it is in the other one. We get 4 atoms per cell in this arrangement. And let's call it a day here. So tomorrow, what we're going to do, tomorrow's plan is after the exam, We're going to talk about some of the calculations and how to do some common kinds of figuring out based on these kinds of arrangements. So we'll be able to do things like, how do we calculate the density of a solid if we know it's packing? How do we determine the atomic radius or the edge length of one of these cubes? There are some definitive relationships that we'll cover there when we do. The other thing that we'll look at tomorrow is we'll start to look at how do these structures start to apply to non-metallic kinds of things. So I made mention this earlier that ionic compounds tend to mimic metallic compounds in their arrangements. We'll show you some examples of how they do that and what it looks like. And we'll also talk about things like semiconductors, which have an important role in a lot of our technology and how they work. So tomorrow we are closing up on chapter 18. But let's go ahead and get one last point in for today. And we'll call it a day here.